Hi, I'm Sathish Kumar Arumugam. Welcome to my project proposal presentation on design of acoustic metamaterials for minimizing total scattering from large rigid object. Acoustic metamaterials are engineered materials that exhibit properties which are not typically found in natural media. These acoustic metamaterials enable unconventional wave control. The scattering from large rigid object leads to acoustic energy loss and performance degradation. Arranging optimized cylindrical scatters around objects can reduce scattering. The image shows optimized scatterers placed around the large rigid object, which reduces the backscattering. A theoretical method is used to bend or control sound waves around an object, which lays the foundation for acoustic clocking. Gradient-based optimization method is developed to optimize scatter position and radius for reducing scattering. Optimization of both position and radius of scatterers is done simultaneously using computational design framework. The hypothesis of this proposed investigation is that designing a non-uniform arrangement of cylindrical acoustic scatterers using gradient-based optimization will significantly reduce the total scattering from large rigid object across a selected range of frequencies. This hypothesis will be tested through computational modeling based on multiple scattering theory. Julia programming is used for simulation and optimization, whereas MATLAB is used for validation and visualization. Major deliverables includes working code files of Julia and MATLAB, schematic drawing showing radii and position of scatterers, plot of scattered energy versus frequency for various configurations. Evaluation metrics. Percentage reduction in total scattering, where higher percentage reduction is better. Computational runtime for optimization in Julia, where lower computation runtime is better. Convergence tolerance achieved in optimization, where lower convergence tolerance is stable. Methodology starts with simulation setup. A 2D acoustic model based on multiple scattering theory is developed, in which center rigid object surrounded by cylindrical scatterers. Gradient-based optimization is used to adjust the position and radius of scatterers for minimizing scattering. The performance of the model is tested across a range of frequencies. The result of trained model is compared with the random configuration model. The output includes plots and scatterer layout diagrams. MATLAB is used for visualization and post-processing. A significant risk is that gradient-based optimization process may produce inaccurate or unstable simulation results due to improper gradients or models. The mitigation strategy is to test the optimization code first using simplified configuration with known outcomes from previous studies and validate it step by step. The contingency plan is to simplify the optimization problem by fixing the radii of the scatters and optimizing only their positions. Also, reducing the number of scatterers might provide good results. Preliminary work includes simulation framework and dataset generation. A two-dimensional simulation environment was implemented in Julia using waves.jl packages, in which a single scatterer m is equal to 1 was used to generate 500 randomized episodes. The model was trained to predict scattered acoustic energy. Then the trained model is integrated into a predictive model control loop using random shooting with 512 candidates per step. The result and visualization includes scatter layout and the plots of scattered energy versus frequency. Figure 1 shows the scatter layout of guided and random configuration, where the guided model exhibits reduced backscattering and the random model has higher backscattering. Scattered energy versus time plot. Here the guided model has reduced scattered energy than the random scatterer. This preliminary work validated the full modeling, training, and control pipeline from dataset generation to controller execution. This forms the basis for future extension involving multi-scatterer, that is M is equal to 10, 12, or 20. Significance builds a system that combines simulation, machine learning, and optimization to control how sound waves moves around object, uses gradients and models to design acoustic clock faster and more accurately than traditional methods, helps create scalable tools for application like noise reduction, stealth, defense, and acoustic research. Thank you for watching.